On April 13th, 2029, a mountain of rock the size of a cruise ship will fall toward you. It will pass closer than the satellites beaming your television. For a few minutes, you will watch it drift across the sky with your own eyes. Its name is Apophis, the god of chaos, and as it nears, Earth's gravity will squeeze it, twist it, spin, maybe crack it open. If wonders like this pull you in, follow along and subscribe. Look up, it is coming. Picture a quiet dome in the Arizona desert on a June night in 2004. Roy Tucker sits at a small telescope on Kitt Peak, scanning for points of light that move. A faint dot slides across his screen, drifting against the still stars behind it. He calls his colleague David Tholen. Together they track it for 2 nights. Then the moon rises bright, the sky glows, and the little dot fades into the glare. They lose it. Half a year passes. The object is out there somewhere, circling the sun, and no one knows exactly where. Then, in December, other astronomers half a world away catch a faint mover of their own. Someone links the 2 sightings. Same rock, same orbit. And the moment those points connect, a computer does what computers do. It draws the path forward. The path came uncomfortably close to Earth. At first the numbers felt like noise, a speck of rock, far away, on a long loop around the sun. Astronomers find these all the time, and almost everyone drifts harmlessly past. So the team fed in more measurements and asked the software to sharpen the answer. Instead of shrinking, the danger grew. Each new night of data pulled the possible impact zone tighter around our planet. They gave it a plain catalogue label at first, a cold, forgettable string of characters. But the thing behind the label refused to stay forgettable. It was wide enough to level a city, it was moving fast, and its orbit crossed our own, like 2 race cars sharing a track at different speeds, looping around and around, their paths kissing at one dangerous point. Here is what made it strange. Most threatening rocks reveal themselves slowly, and the worry eases as we learn more. This one did the opposite. The more carefully the astronomers looked, the more it seemed to lean toward us. Word spread through the small world of asteroid hunters. Emails flew between observatories in different countries. People checked each other's math, hoping someone had made a mistake. Nobody had. By the final days of 2004, a handful of scientists were staring at a possibility they had trained their whole lives to detect and hoped never to see. A large asteroid, freshly rediscovered, with a real and rising chance of striking Earth within a single human lifetime. The date the models kept circling sat only 25 years away, close enough that many people alive to read the warning would still be alive to watch it arrive. The astronomers needed to be sure, so they raced to gather every scrap of data before the rock swung out of view again. Every measurement mattered, every hour counted. Because a number was climbing on their screens, a single number that would soon reach every space agency on the planet. That number measured the odds that the sky was about to fall, and when it peaked, it would break a record no one wanted to break. But before the world learned the odds, the object needed a proper name. And the name they chose was almost a dare, pulled from an ancient story about darkness swallowing the sun. The 2 men who found it got to choose what it would be called. That is the quiet privilege of discovery. Find a new world, and you name it. Most asteroids end up with the names of scientists, cities, or loved ones. This one earned something darker. They reach back thousands of years, to ancient Egypt, to a monster the old stories feared above all others. Every night the Egyptians believed the sun god sailed his boat across the sky, and every night a giant serpent lay waiting in the dark to swallow him whole. That serpent had a name, Apophis, the bringer of chaos, darkness and destruction, the enemy of light itself. You can see why the name fit. Here was an object that might one day blot out part of our sky and rain fire on our cities. Naming it after the serpent that eats the sun was almost too perfect. It carried a warning in a single word. There was a second reason too, a lighter one the discoverers admitted with a grin. Both men were fans of a science fiction show, and one of its most memorable villains also went by Apophis. So the name honoured an ancient god and a modern story at once. A monster from the dawn of human imagination, and a monster from a television screen. The public loved it. Reporters latched onto the phrase right away. The god of chaos. It sounded like a movie. It sounded like the end of the world. and for a brief tense stretch of time, scientists worried it might be exactly that. Giving a threat a fearsome name is a double-edged thing. On one hand, it grabs attention, and attention brings funding, telescopes, and careful study. On the other hand, a scary name can twist the truth. People hear God of Chaos and picture doom, even after the doom has passed. The rock became a symbol long before anyone finished measuring it. Its name did half the storytelling on its own. The astronomers, though, were naming a specific physical object with a specific size and speed. And to understand why they reached for the god of destruction, you have to understand what this thing could actually do. A rock this wide, moving this fast, carries an almost unimaginable punch. By the standards of space, where whole moons drift by, Apophis counts as small, a single stadium of stone. The danger hides in the speed. An asteroid the size of Apophis would slam into the atmosphere faster than any bullet humans have ever fired. All that motion has to go somewhere in an instant. It turns into heat, light, and a shock wave that can flatten everything for miles around the point of contact. The name matched the physics. It was a fair description of the energy locked inside this quiet, tumbling rock. So they had a name worthy of the threat. What they needed next was a number worthy of it too. A cold, precise way to measure just how likely this god of chaos was to keep its terrible promise. And when that number arrived, it climbed higher than any asteroid had climbed before. In the last week of 2004, a small group of scientists watched a number rise on their screens and felt their stomachs drop. The number measured one thing: the chance that Apophis would hit Earth on its close pass in the year 2029. It started low, the way these things usually do, a fraction of a percent, barely worth a headline. Astronomers see values like that often, and they almost always fade to nothing once more measurements roll in. So the team did the normal thing. They gathered fresh observations and expected the risk to melt away. It refused. Each new night pushed the odds up instead of down, from a whisper to a worry. The chance of impact climbed past 1%, a threshold that sets off quiet alarms in the asteroid community. Then it kept going. It passed 2%, it reached roughly 2.7%, and there it hovered, glaring back at the people trying to make it disappear. 2.7%. Say it out loud and it sounds almost harmless. Flip it around though, and the meaning sharpens. 2.7% is about 1 chance in 37. Imagine a bag holding 37 marbles and only one of them painted red. Reach in without looking and pull one out. That is the chance the scientists were staring at. 1 red marble in the bag, and the red marble meant a city-killing rock arriving on a known date. For an asteroid this large, those were the worst odds anyone had ever confirmed. These were tense days inside a very small world. The people who track dangerous asteroids mostly know each other. They share data, argue over decimal points, and trust one another's instruments. Now they were double-checking a result none of them wanted to be true. Every fresh measurement of that faint dot either tightened the noose or loosened it, and for a while it kept tightening. The clock made it worse. Apophis was drifting toward a stretch of sky where the sun's glare would soon hide it. A window was closing. If they could not gather enough data before the rock vanished, the frightening odds might sit there, unresolved, for years. A 1 in 37 threat frozen on the books with no way to prove it wrong until the object returned to view. So telescopes around the world turned toward the same patch of darkness. Astronomers begged for observing time. They hunted through old images too, archived photographs where Apophis might be hiding, unnoticed, from months or years before. Every extra data point stretched the known path of the asteroid and made the prediction sharper. The whole effort came down to a simple race. Measure the rock precisely enough, fast enough, to learn whether that red marble was really in the bag. While they worked, the wider world started to notice. The story leaked into the news. A giant asteroid, a real chance of impact, a date within reach. And to help everyone understand how serious it was, scientists pointed to a special scale built for exactly this purpose, a ladder of danger, from harmless at the bottom to catastrophe at the top. Apophis was about to climb higher on that ladder than any asteroid before it. Scientists needed a way to talk about asteroid danger without spreading panic. So years earlier they built a simple ruler for exactly this moment. It runs from 0 to 10. 0 means no worry at all. a rock that will miss us by a mile or drift harmlessly through the dark. 10 means a certain civilization-ending collision. Every level in between carries its own shade of concern, like the colours on a weather map sliding from calm green to angry red. For almost every asteroid ever measured, the ruler reads 0, harmless, move along. A handful have nudged up to 1 or 2, enough to keep watching, never enough to lose sleep. Before Apophis, no large asteroid had climbed higher than that and stayed there. Apophis reached 4. 4 does not sound dramatic, sitting in the middle of a 10-point scale. The meaning behind it was heavy. A level 4 means a real close encounter with a genuine chance of a regional disaster, serious enough that astronomers must pay very close attention. No asteroid had ever earned that rating before, and none has matched it since. For a short, strange window at the end of 2004, this single rock held a record in the history of planetary danger. The record put real pressure on the scientists to resolve it fast, a number that high demanded either proof of a hit or proof of a miss. Sitting in the frightening middle was the one outcome nobody could accept. Relief came from an old habit of astronomy. Photograph the sky often enough and you capture things before you even know they matter. Somewhere in the archives, in images taken months earlier, Apophis was lurking, a faint smudge nobody had flagged. When researchers dug out those older pictures and added them to the fresh ones, the known path of the asteroid stretched backward in time. A longer path means a sharper prediction. Suddenly the math had far more to work with. The sharpened path swung the answer the good way. With the extra data folded in, the frightening close pass in 2029 snapped into focus. Apophis would come startlingly near. It would miss. The odds of a strike on that date collapsed from 1 in 37 all the way down to 0. The record-breaking rating on the danger scale dropped like a stone, back toward the calm green bottom where almost every asteroid belongs. You could almost hear the exhale from observatories around the world. The immediate nightmare had ended. Yet a smaller thread of worry still dangled. When Apophis swings past us in that famous flyby, Earth's gravity will bend its path. Depending on exactly where it passes, our planet's pull could aim it toward a future collision, years or decades later, on another loop around the Sun. So even after 2029 was cleared, faint question marks hovered over dates further ahead. Little windows of risk, waiting to be closed. Closing them for good would take a new kind of look. A beam of energy fired across millions of miles of empty space, bouncing off the rock and returning with an answer. That beam was radar. And in 2021 it would finally settle the question of Apophis for 100 years. To kill the last of the fear, scientists needed to know exactly where Apophis sat in space. Telescopes that only catch sunlight can measure an asteroid's position well, though never perfectly. There is a sharper tool, radar. Here is the beautiful, simple idea behind it. Point a giant dish antenna at the asteroid and fire a beam of radio energy straight at it. That beam races across space at the speed of light, strikes the rock, and bounces back. Catch the faint echo, time it to the tiniest fraction of a second, and you can measure the distance to the asteroid with stunning precision. You can even watch how fast it moves toward or away from you. The rock becomes less of a guess and more of a known thing, pinned in space like an insect under glass. In the spring of 2021, Apophis gave astronomers a chance to try. The asteroid swept through the inner solar system on one of its regular passes, still far away, about 10 million miles out. That is more than 40 times the distance to the Moon, a huge gap by everyday standards. For radar, it was close enough. Enormous dish antennas in California and West Virginia turned toward the rock and sent their beams into the dark. The echoes came back. From those faint returning whispers, scientists measured the position of Apophis better than ever before. They watched it move. They fed the new numbers into their models and asked the old nagging question one more time. Could this rock, on any of its future passes, strike Earth? The answer came back clean. Apophis would miss. It would miss in 2029. It would keep missing through the worrying years that followed, and it would keep missing for a full century to come. That word, century, matters. Remember those faint windows of future risk, the ones left dangling after the first scare eased? The radar closed them. Everyone, The distant dates that had kept a thread of worry alive were wiped off the risk list entirely. For the first time since its discovery, Apophis carried no official danger at all. Scientists even removed it from the special table where they track hazardous rocks. The god of chaos had been officially declawed. You might expect that to be the end of the story, a scary asteroid, found, feared, and finally cleared. Time to look away and move on to the next threat. The scientists did the opposite. They leaned in closer, because clearing Apophis of danger did something unexpected. It turned a threat into a gift. This same rock, the one that had frightened the world, was still going to make the closest pass of any asteroid its size in recorded history. It would still skim just above our heads in 2029. Only now, instead of dreading that moment, scientists could look forward to it. A front row seat to a giant asteroid, sweeping by close enough to touch, with no fear attached. That flyby would become one of the most anticipated events in the history of space science. Telescopes on the ground and spacecraft in the void would all turn toward a single point in the sky on one specific spring evening. And billions of people would be able to look up and see it happen with their own eyes, without a telescope, without binoculars, just a naked eye turned to the stars. What that night will actually look like is stranger than most people expect. Mark the date, April 13th, 2029, a Friday evening. On that night, for the first time in recorded history, a large asteroid will be visible to millions of people using nothing but their own eyes. Think about how rare that is. Space holds countless millions of asteroids, and almost none ever become visible to us. They are too small, too dark, or too far away. To see one without a telescope, it has to pass extraordinarily close. Apophis will pass that close. For a few hours, a chunk of rock as tall as a skyscraper will hang in our sky as a moving point of light, and a huge share of humanity will be able to step outside and watch it go by. The show will favour one half of the planet. Observers across Europe, Africa, and much of Asia will get the best view, with the asteroid riding high enough in their evening sky to spot easily. Billions of people live under that stretch of sky. Cities, villages, deserts, and coastlines, all facing the same direction, all able to look up at the same traveller at the same moment. Now, a word of honesty about what you will see. Apophis will look like a faint star. It will glow at about the brightness of a modest star, roughly 3 times dimmer than Polaris, the famous North Star that guides sailors, so it will hide from the worst of city glare and shine best from a dark spot far from streetlights. Nobody should expect a blazing streak. Meteors flare because they burn up in our air, close and fast. Apophis will stay thousands of miles above the atmosphere, gliding rather than flaring. The wonder lives in the meaning more than the brightness. When you find that pale dot and lock your eyes on it, you will be staring at a solid world, a piece of the early solar system, older than any life on Earth, and it will be racing past your planet at a distance smaller than the width of some countries. That knowledge changes how the little light feels. A faint point becomes a giant. A quiet evening becomes a brush with something ancient and enormous. There is a shared human quality to it that scientists love. This event throws its doors open to everyone. Anyone under the right sky can join in, with no expensive equipment and no mountaintop dome required. A child in one country and a grandparent in another, both tilting their heads back, both watching the same rock. Moments that unite that many strangers around a single point of light come along only a few times in a lifetime. Astronomers are already planning viewing parties, apps, and guides to help people find it. They want as many eyes on the sky as possible, partly for the joy of it, and partly because moments like this pull people towards science in a way no textbook ever could. A real object, a real date, a real thing you can point at. Yet the ground view is only half the marvel. The truly astonishing part is how close Apophis will actually come, close enough to slip beneath our own machines, inside the ring of satellites that circle our planet every day. And that raises an unsettling question. How does a rock that big fit underneath our own technology? That's chapters 1 through 6. Say, continue, and I'll pick up with chapter 7 on the strange geometry of the flyby. Every day, a ring of machines circles our planet far overhead. The most useful ones ride in a special orbit about 22,000 miles above the ground. At that exact height, a satellite loops around Earth in perfect step with our spin, so it appears to hover over one fixed spot. That is where we park the satellites that carry television, phone calls and weather images, a wide, invisible band of technology, always turning above our heads. On April 13th, 2029, Apophis will pass closer than that ring. Let that settle for a moment. This asteroid will sweep within roughly 20,000 miles of Earth's surface. The busy band of communication satellites orbits a little farther out than that. So for a brief window, a mountain of ancient rock will fly beneath our own machines, dipping inside the ring of technology we built to encircle our world. To feel how strange that is, compare it to the Moon. Our familiar companion sits about 240,000 miles away, and it has felt close and comforting to humans for all of history. Apophis will come nearly 12 times closer than that. Shrink the whole gulf between Earth and the Moon down to the length of your arm, and Apophis will pass at the width of a few fingers from your shoulder. A natural fear pops up here. If the rock flies through the same zone as our satellites, will it smash into them? The honest answer brings relief. Space up there is enormous, and the satellites, for all their importance, are tiny and spread thinly across a vast volume. Picture a single grain of sand drifting through a stadium. The odds of Apophis striking any satellite are almost nothing. It will thread through the region like a needle finding a gap in an enormous, mostly empty net. The closeness still matters, and here is why. When a large object passes this near, our planet stops being a bystander. Earth becomes a force acting directly on the asteroid. At 20,000 miles, our gravity does more than watch Apophis go by. It reaches out and takes hold. That grip will bend the asteroid's path. It will speed the rock up as it approaches and swing it around like a stone on an invisible string. The Apophis that leaves our neighbourhood will follow a different orbit than the one that arrived. In a single afternoon, our world will reshape the future of a body that has circled the Sun, undisturbed, for billions of years. Scientists find that thrilling. A close pass this precise, this well predicted, lets them watch gravity work on a real object at a scale they can measure. Every wobble in the asteroid's motion afterward becomes a clue about its hidden insides. The flyby turns Earth into a giant instrument, and Apophis into the sample it tests. So the closeness carries two gifts at once. It hands billions of people a chance to see an asteroid with their own eyes, and it hands scientists a rare, natural experiment they could never run on purpose. A giant rock, passing near enough to feel our pull on a date circled years in advance. Standing under that evening sky, you will not sense any of the gravity at work. You will simply see a faint light. Yet that light will behave in a way no star ever does. It will move. Find a star tonight and stare at it. It holds perfectly still. Watch for a minute, 5 minutes, an hour, and it stays fixed in place, drifting only with the slow turn of the whole sky. That stillness is what makes a star a star. On the night of April 13th, 2029, one point of light will break that rule completely. Apophis will move while you watch. This is the detail that separates it from everything else up there, and it is the surest way to know you have found it. Most objects in the night sky creep so slowly that your eye cannot catch the motion at all. Apophis will be so close that it crosses the sky quickly, gliding along at a pace you can actually see in real time. In roughly a minute, it will shift by about the width of the full moon. Watch a patch of sky, and the little light will slide steadily out of one spot and into another while you hold your gaze. That kind of motion feels almost alive. A wandering light sliding past the fixed stars, refusing to sit still. You might wonder how to tell it apart from an airplane or a passing satellite. The clues are simple. An airplane blinks, shows coloured lights, and often crosses the whole sky in a couple of minutes. A low satellite races even faster and usually fades out as it slips into Earth's shadow. Apophis will glow with a steady, quiet light, no blinking, no colour, and it will drift at its own measured pace, far higher and slower than any human machine. Once you notice that patient, unblinking glide, you will not mistake it for anything else. Think about what that motion really shows you. The stars appear frozen because they sit unimaginably far away. so far that even their true enormous speed seem to vanish. Apophis will seem to move for the opposite reason. It will be so near that its real journey through space becomes visible to you, unfiltered with your own eyes. The drift you see is the raw motion of a solid world sweeping past your planet. For skywatchers, the plan will be straightforward. Astronomers will share maps and apps showing exactly where to look and when, hour by hour for each part of the world. Find a dark spot away from city lights. Let your eyes adjust to the dark for a while, then look toward the marked patch of sky and wait for the star that will not stay put. When you catch it, pause and hold the moment. That slow-moving speck is a piece of rock as tall as a skyscraper, closer to you than the machines that carry your phone calls, moving fast enough to see. People have looked up at the night sky for tens of thousands of years. Almost none of them ever watched an asteroid pass. You will. There is a quiet reason astronomers care so much about getting the whole world to look. A shared sky moment like this pulls people toward wonder, and wonder is where curiosity begins. A moving light can turn a bored teenager into a future scientist in a single evening. Yet as you watch that faint dot slide by, it hides its true scale. The light looks small and gentle. The object behind it is anything but small. That faint drifting light will fool you. It will look tiny, a modest speck among the stars. The rock behind it is a giant. Apophis measures roughly 1,000 feet across, close to 340 meters. Picture a cruise ship standing on its end, or the Eiffel Tower laid on its side, or 3 football fields lined up nose to nose. That is the width of the quiet dot moving through your sky. In the scale of space, a rock this size counts as small. Whole moons and planets dwarf it. Yet on the human scale, on the scale of cities and buildings and the ground under your feet, it is enormous. If Apophis stood in the middle of a downtown, it would loom over every skyscraper around it. This is a mountain, flying free. Now hold that size next to the asteroids that have actually struck Earth in recent memory, and the danger it once posed snaps into focus. In 2013, a small rock streaked over the city of Chelyabinsk in Russia. It measured only about 60 feet across, roughly the length of a school bus. It never even reached the ground. It exploded high in the air, and still that airburst shattered windows across the city and injured well over 1,000 people who were standing too near the glass. A bus-sized rock did that just by blowing up in the sky. Go back further, to the year 1908, deep in the forests of Siberia. An object thought to be around 150 feet wide exploded above a remote region called Tunguska. The blast flattened an estimated 80 million trees across an area larger than many cities. Had it arrived over a populated place, it would have erased that place entirely. Apophis dwarfs both of those. It stretches something like 6 times wider than the Tunguska object, and a rock's destructive power grows far faster than its width. Doubling the size of an asteroid multiplies its energy many times over, so Apophis does not carry 6 times the punch of Tunguska. It carries vastly more. A strike from a rock this large would not level a forest or a single city. It would devastate an entire region, wiping out everything for many miles and sending shockwaves far beyond. That is why the early scare felt so heavy. The scientist was staring at a proven city killer with a real chance of arriving on a known date. The relief when they cleared it was earned. There is a strange comfort in the size too. Because Apophis is large, we can see it, track it, and predict it with great precision. The truly frightening asteroids are often the smaller ones we cannot spot until they are almost here. A rock big enough to threaten a region is also big enough to reveal itself years in advance, giving us time to measure it and one day, to act. Apophis is a giant we can watch. We know its size, we know its path, we even know the date it will visit. Yet one basic question about it remains oddly open. What is this mountain actually made of? The answer hides in the colour of its light, and that colour tells a story about a violent ancient past. You cannot fly out to Apophis with a hammer and chip off a sample. Yet scientists can still learn what it is made of from millions of miles away. The trick lies in its colour. When sunlight bounces off an asteroid, the rock absorbs some shades and reflects others, depending on the minerals inside it. Spread that reflected light into a rainbow, study which colours are missing, and you can read the recipe of a world you have never touched. Read Apophis this way, and it falls into a well-known family. It is a stony asteroid, rich in the same silicate minerals that build ordinary rock here on Earth. Its makeup closely matches the most common kind of meteorite that falls to our planet, the plain stony chunks that land in fields and deserts every year. So Apophis is not exotic or metallic. It is a familiar sort of stone, the everyday building material of the inner solar system. That ordinariness carries a puzzle inside it, and the puzzle is where things turn strange. Space is a harsh place for a surface. Out in the open, an asteroid gets blasted for millions of years by tiny particles streaming from the sun and by micro-sized bits of dust travelling at brutal speeds. This constant bombardment slowly darkens and reddens the rock, like skin weathering under a relentless sun. Old, undisturbed asteroid surfaces should look aged and worn in a very specific way. Scientists call this slow darkening space weathering. Apophis looks fresher than it should. Its surface shows the colours of relatively young unweathered rock, as if parts of it were exposed only recently. That raises an obvious question. How does an ancient asteroid, billions of years old, keep a face that looks freshly turned? Something must be scraping away the old weathered skin and revealing clean rock beneath. Something must be resurfacing it. Astronomers have a leading idea, and it ties directly to the reason Apophis is so famous. Close passes near planets. When an asteroid swings near a world like Earth, the planet's gravity can shake its surface, shift its loose material, and expose fresh rock underneath. Over a long history of near misses, these gravitational jolts may keep wiping the asteroid's face clean, resetting its colour again and again. If that idea holds, then Apophis is a perfect test case. It is about to make one of the closest passes ever recorded. If close encounters truly refresh asteroid surfaces, then this flyby should do exactly that, right in front of our instruments. Scientists could watch the resurfacing happen, leave, and finally confirm an idea they have only been able to guess at from a distance. That turns Apophis from a mystery into an experiment. Its young-looking face is both a clue about its violent planet-brushing past and a promise about what the 2029 flyby might reveal. A stony rock that keeps renewing its skin and a close pass that might catch it in the act. To understand how a flyby could shake a surface clean, though, you first have to understand how this rock moves through space. And here Apophis breaks another rule. It does not spin the way a normal world spins. It tumbles. Most worlds spin cleanly. Earth turns around a single steady axis, an invisible line running from the North Pole to the South Pole, and that line stays fixed as we rotate. Day follows night in a smooth, reliable rhythm because our spin behaves itself. Nearly every planet and moon does the same. Pick an axis, turn around it, keep it simple. Apophis refuses. This asteroid does not spin around one steady line. It tumbles, rolling and pitching through space in a complicated, off-kilter motion that never quite repeats. Picture a football thrown badly by someone who cannot make it spiral. Instead of turning smoothly point first, it wobbles end over end, twisting as it flies, flashing a different face at you with every heartbeat. That is Apophis, only far larger and moving through the endless dark. Scientists have a name for this messy motion. They call it tumbling, or non-principal axis rotation. It means the asteroid's spin and the line it wants to turn around have fallen out of agreement. The rock leans away from its own axis by a wide angle, more than 30 degrees, and stays stuck in that awkward, wobbling roll. Point yourself at Apophis and wait, and you would see it present a constantly shifting profile, its long shape swinging and pitching in a way that feels almost dizzy. Why does it move like this? A clean, simple spin is actually the calm, settled state a rock reaches after a long, peaceful history. Tumbling suggests the opposite. It hints that something disturbed Apophis, and that the rock has not yet had time to settle back into an orderly turn. A collision long ago or a close brush with a planet could have knocked it into this restless wobble. In that sense, the tumble itself is a memory. It is the asteroid still shaking from some ancient shove. There is a deeper clue hidden in the wobble. The way a rock tumbles depends on how its weight is spread inside. A solid, evenly packed stone tumbles one way. A lopsided rock or a pile of rubble loosely held together tumbles another. So by studying this awkward motion carefully, scientists can begin to guess at the hidden structure of Apophis, the parts they cannot see. The tumble becomes a window into the insides. This matters enormously for the flyby. When Earth's gravity grabs Apophis in 2029, the effect on its spin will depend on exactly how the rock is tumbling and exactly how its mass is arranged. A steady spinner would respond in a clean, predictable way. A tumbler like Apophis will respond in a far more complex one. Our planet is about to reach out and interfere with an already restless motion, and the result could be dramatic. To watch that happen, scientists first had to measure the tumble as it is now, before the encounter changes it. They studied the asteroid's flickering brightness over many nights, tracking how its light rose and fell as different faces turned toward us. From that flicker, they reconstructed the wobble and pinned down its rhythms. What they found sounds almost impossible. Apophis carries two different clocks at once, and the two do not agree. One of them ticks so slowly that a single turn stretches longer than a week. Here on Earth, time in the sky feels simple. The sun rises, crosses overhead, and sets. One spin, one day, roughly 24 hours over and over. Our single clean rotation gives us a single steady clock. On Apophis, that simplicity falls apart completely because the tumbling rock keeps two clocks running at the same time. Start with the slower one. Apophis takes an astonishingly long time to complete one full turn about its long axis. Not hours, not a single day. It needs around 11 days to finish one rotation. Imagine standing on its surface and waiting for the sun to travel across your sky just once. You would wait longer than a week for a single asteroid day. The rock turns with a slow, ponderous grace, dragging its long shape around in no hurry at all. Now add the second clock, and this is where it gets truly strange. On top of that slow 11-day turn, the whole asteroid also wobbles, and that wobble has its own rhythm of a little over a day, roughly 27 hours. So while the rock inches through its long, slow rotation, it is simultaneously nodding and swaying on a faster beat, like a spinning top that leans and circles even as it turns. Two motions, two clocks, one slow and stately, one quicker and wobbling, layered on top of each other and never lining up. For anyone standing on the surface, the sky would become a puzzle with no simple answer. The sun would not rise and set on any neat schedule. It would loop and drift through the heavens in a tangled, ever-shifting path, driven by two overlapping cycles at once. Days and nights would come in strange, uneven stretches, different every time. The comforting rhythm we take for granted here would simply not exist there. This double clock is a direct result of the tumble from the last chapter. A clean spinner has one clock. A tumbling rock has this layered, two-cycle motion, because its spin and its wobble run on separate tracks. So the very complexity of the timekeeping is another sign of how disturbed and restless Apophis really is. The two clocks also give scientists something precious, a measuring stick. Because they now know these rhythms so precisely, they can watch for any change in them after the flyby. If Earth's gravity alters the way Apophis tumbles, the clocks will shift. The 11-day turn might speed up or slow down. The wobble might grow or shrink. By comparing the timing before and after, researchers can measure exactly how much our planet disturbed the rock. That is the quiet power of knowing the current motion so well. It turns the asteroid into a before and after experiment. Whatever the encounter does, the changed clocks will record it, and careful tracking will read that record back to us. So we arrive at the heart of the story. A stony, tumbling giant, keeping two mismatched clocks, is about to fly closer to Earth than our own satellites, and when it does, our planet will not simply watch it pass. Earth is going to reach out across 20,000 miles of empty space and physically take hold of it. To see how a world can grab a rock it never touches, you have to understand the strange invisible force that does the grabbing. Gravity has a secret that most of us never think about. Its strength depends sharply on distance. Move closer to a massive object, and its pull grows fast. Move farther away, and the pull fades just as quickly. This simple rule sits quietly behind everything that is about to happen to Apophis. Right now, as Apophis circles the sun far from us, Earth's gravity barely touches it. Our planet is just a distant point, too far away to matter to the asteroid's path. But on April 13th, 2029, Apophis will dive to within about 20,000 miles of our surface. At that range, Earth stops being a distant point. It becomes a giant looming presence, and its gravity surges into a powerful grip. Earth will reach out with invisible hands and take hold of the asteroid. The first thing that grip will do is bend the rock's journey. As Apophis rushes in, our gravity will pull it, curving its straight-line flight into a tight, swinging arc. The asteroid will accelerate as it approaches, whip around our planet, and then race away on a new heading. Think of a stone tied to a string, swung around your hand and then released. It leaves in a different direction than it arrived. Earth will do the same to Apophis, using gravity instead of string. That single swing will rewrite the asteroid's future. The orbit it follows around the Sun after the flyby will differ from the one it followed before. Its path, its timing, its whole schedule of future passes, all reshaped in a matter of hours by one close encounter. A rock that has looped the Sun in the same steady way for billions of years will leave our neighbourhood on a changed course. There is a second, subtler effect, and this is the one that could transform the asteroid itself. Because gravity weakens with distance, the side of Apophis facing Earth will feel a stronger pull than the side facing away. The rock is wide, 1,000 feet across, so its near side and its far side sit at slightly different distances from us. Slightly different distances mean slightly different pulls. Our gravity will yank harder on the close face than on the far one. That uneven tug is the key to everything that follows. It is the same kind of force the moon uses to raise the ocean tides here on Earth. A gentle, lopsided pull that stretches whatever it acts on. Scientists call it a tidal force, and during the flyby, Earth will apply it to a solid rock. For most of the asteroid's long life, no force like this has touched it. Out in deep space, far from any planet, Apophis drifts in peace, every part of it pulled equally by the faint, distant Sun. The close pass shatters that peace. For a few dramatic hours, our planet will grip the rock unevenly, straining it in a way it has almost never felt before. What does an uneven pull do to a mountain of stone? That depends on how tightly the mountain holds together, and that is exactly what scientists ache to find out. A solid, welded rock would shrug off the strain. A loose pile of rubble might shift, slide, and rearrange. To predict the outcome, they have to look closely at that lopsided pull, the stretch and squeeze of a tidal force, and imagine what it could do to a rock we have never touched. Return to that lopsided pull because it does something more interesting than simply bending the asteroid's path. It changes the asteroid's shape, or at least it tries to. During the flyby, Earth's gravity will grab the near side of Apophis harder than the far side, and that difference will stretch the whole rock along the line pointing toward our planet. Imagine holding a soft ball of dough in one hand. Pinch the far end and pull, while the near end lags behind, and the dough stretches out into an egg shape. Earth's uneven gravity will try to do the same to Apophis, elongating it slightly toward us as it passes. At the same time, the sides of the rock get gently squeezed inward, stretched in one direction, pinched in the others. This stretch and squeeze is the signature of a tidal force. You already know this force, even if you have never named it. It is the very same effect that drives the ocean tides. The moon pulls a little harder on the ocean facing it than on the solid Earth behind it, and harder on the near ocean than on the far side. That difference raises the water into bulges, and as our planet spins beneath them, coastlines rise and fall in the daily rhythm of the tides. What the moon does to our seas, Earth will briefly do to Apophis. Water bulges easily, of course, because it flows. A solid rock resists. So the real question becomes a contest of strength. On one side, Earth's tidal pull, straining to stretch the asteroid. On the other, the internal strength of the rock holding itself together. Which one wins depends entirely on what Apophis is made of on the inside, and that remains one of the great unknowns. Consider the possibilities. If Apophis is a single, solid slab of welded stone, it will hold firm. The tidal strain will be far too weak to crack a rock that strong, and the asteroid will ride through the flyby with its shape intact. But if Apophis is something looser, the story changes. Many asteroids are not solid at all. They are rubble piles, great heaps of boulders, gravel and dust held together only by their own faint gravity, with almost nothing binding them beyond that gentle self-attraction. For a rubble pile, even a weak tidal tug becomes meaningful. The pieces are barely holding hands. A lopsided pull could loosen that grip, letting boulders shift, slopes give way, and loose material slide across the surface. The rock would not shatter, yet it might rearrange, settling into a slightly new form as it swings past us. This is why scientists are so hungry to know the asteroid's inner structure, and why the flyby is such a gift. The tidal strain of 2029 is like a doctor gently pressing on a patient to feel what lies beneath the skin. By watching how Apophis responds to the stretch and squeeze, researchers can finally sense whether it is solid rock or loose rubble, a secret hidden from us since the day it was discovered. The stretch is only the setup. The truly dramatic possibility is what that strain might unleash on the surface itself. A world where a gentle pull could set loose material moving, where slopes already teetering on the edge might finally let go. Earth's passing grip might trigger a quake on another world. Think about what it would take to shake a mountain in the sky. On Apophis, it might take surprisingly little. If the asteroid is a loose pile of rubble, its surface is a delicate thing, a landscape of boulders and dust resting at the very edge of stability. Gravity there is almost nothing, barely a whisper compared to the pull that holds you to Earth. In that fragile world, even a small nudge could set things moving. The flyby will provide the nudge. As Earth's tidal force stretches and strains the asteroid, it will send that stress rippling through the rock and across its surface. Scientists believe this could trigger events that sound almost impossible on a body so small. Quakes, landslides, loose material sliding downhill in eerie slow motion. For a brief window during the close pass, Apophis could come alive with motion, its surface shifting and settling under the strain. Picture a slope on the asteroid, a gentle rise of gravel and dust that has sat undisturbed for ages, balanced right on the edge of sliding. Under normal conditions, nothing moves it. Then Earth's gravity reaches in and adds just enough extra pull, and the balance tips. The slope lets go. In the feeble gravity of Apophis, the landslide would not crash down the way it would here. It would drift. Boulders would float lazily downslope. Dust would rise in slow, hanging clouds, and the whole event would unfold with a strange, dreamlike calm. An asteroid quake would be just as gentle and just as profound. There would be no roaring, no violent shaking as we know it. Instead, the rock would shudder faintly, its loose pieces resettling, its surface rearranging itself grain by grain and boulder by boulder. Quiet, slow, and utterly alien. Here is why scientists find this so thrilling. These very events could be the answer to the puzzle from earlier, the mystery of why Apophis looks so young. Remember, its surface appears freshly exposed, as if something keeps wiping away the old weathered skin. Landslides and shaking during close passes could be that something. When the surface slides and settles, it buries the old sun-darkened material and reveals clean rock beneath. The flyby might catch this resurfacing in the act, solving a riddle scientists have puzzled over for years. There is a deeper prize still. Watching how Apophis shakes would reveal what it is made of inside. A solid rock and a loose rubble pile would respond to the strain in completely different ways. So every quake, every slide, every drifting boulder would carry information about the asteroid's hidden interior, structure we have never been able to see. The surface, in moving, would tell us about the depths. All of this depends on catching the moment as it happens. These changes would not unfold slowly over days. They would strike in a narrow window, right around the closest approach, when the tidal strain reaches its peak. Miss that window, and you miss the show. The asteroid would settle back into stillness, its secrets locked away for another lifetime. So scientists have zeroed in on the exact stretch of time when Apophis is most likely to transform, and their models point to a startling possibility. In a window of only about half an hour, a piece of the asteroid's face may be reborn. Timing is everything for the scientists watching Apophis. The changes they hope to see will not creep in slowly over the days around the flyby. They will strike in a sudden, narrow burst, right at the moment the asteroid comes closest and Earth's grip is strongest. Blink at the wrong time, and the whole transformation could slip past unrecorded. So researchers built detailed computer models, feeding in everything they know about the asteroid's size, shape, tumble, and likely makeup. Then they asked a sharp question. When exactly will Apophis change, and how much of it? The answer that came back surprised even the people who ran the simulations. One careful model predicts that roughly 1 out of every 100 parts of the asteroid's surface could be resurfaced, and it predicts this will happen in the span of about half an hour, striking close to 30 minutes before the moment of closest approach. A single, brief window in which part of a world quietly remakes its face. Sit with that image for a moment. For countless ages, a patch of Apophis has worn the same old weathered skin, darkened by eons of sunlight and space dust. Then, in a half-hour flung across a single spring evening, that patch shifts, slides, and turns over, exposing fresh rock that has never seen the sun. An ancient surface, rewritten in less time than it takes to watch a short film. The models also agree on where the action concentrates in time. The strongest disturbances happen within hours of the closest pass, not long before and not long after. Far from Earth, the tidal strain is too weak to do much of anything. Only in that tight window near closest approach does our gravity press hard enough to move loose material and reshape the surface. The whole drama plays out in a brief fierce crescendo, then fades. This creates a real challenge and a real thrill for the people watching. To capture the resurfacing, they must observe Apophis continuously through the critical hours, ready to catch the exact instant the surface moves. There is no rewind. The event happens once, live, and then it is over. Every telescope and every spacecraft aimed at the asteroid has to be watching at precisely the right time. It is worth being honest here. Not every model agrees on how dramatic the changes will be. Some simulations suggest the flyby may barely disturb the surface at all, especially if Apophis turns out to be more solid than expected. The true outcome depends on details we simply do not know yet. The strength of the rock, the way its weight is spread, the exact geometry of the pass. That uncertainty is the whole point. Nobody knows, and the only way to find out is to watch. That is what makes this event a genuine experiment rather than a prediction. Scientists have laid out their competing guesses, from dramatic resurfacing to almost nothing, and the flyby will finally judge between them. A half hour of close observation could settle debates that have run for years. The surface is only part of the story, though. The same tidal grip that might rearrange the asteroid's face could reach deeper still, into the very spin of the rock. And on that front, the models predict something even more dramatic. Earth's pull might grab the tumbling asteroid and change how fast it turns. The flyby could do more than shake the surface of Apophis. It could reach into the deepest part of the asteroid's behavior, its spin, and change it. This is one of the boldest predictions scientists have made about the encounter, and it captures just how powerful a close pass with Earth can be. Recall how Apophis moves. It tumbles, rolling through space in that restless wobbling motion, keeping two mismatched clocks at once. That whole complicated dance depends on the rock spinning at a certain rate. Now imagine Earth's uneven gravity grabbing the tumbling giant as it swings by. The lopsided pull will not act evenly across the rock. It will twist it, applying a subtle torque, the same kind of turning force you use when you spin a top or twist open a jar. That twist could rewrite the asteroid's spin entirely. Here is the prediction that stops scientists in their tracks. Depending on exactly how Apophis is oriented as it passes and how its weight is arranged inside, the encounter could change its effective spin rate dramatically. In some scenarios, the rock could end up spinning about twice as fast as before. In others, it could slow to about half its former rate, doubled or halved in a single afternoon. A spin that has held steady across ages, transformed in the hours of one close pass. Think about how strange that is. Apophis has kept its tumbling rhythm for a very long time, its two clocks ticking away undisturbed in the quiet of deep space. Then it brushes past our planet, and it leaves turning at a completely different pace. The 11-day rotation and the day-long wobble could both shift, resetting the asteroid's sense of time. It would be, in a real sense, a different world afterward, moving to a new beat. The exact outcome hangs on details we do not yet know, and that uncertainty is the exciting part. The change in spin depends heavily on the precise angle at which Apophis meets Earth and on how its mass is distributed inside. A rock with its weight bunched toward one end would respond one way. A more evenly balanced rock would respond another. So the spin change is not just a curiosity, it is a message encoded in motion about the hidden structure of the asteroid. That is why scientists are so eager to measure the spin both before and after the flyby. They already know the current rhythm with great precision, thanks to years of patient study. If they can measure it again once Apophis has passed, the difference between the two will reveal how our gravity gripped it, and through that, what the rock is made of inside. The change in spin becomes a fingerprint of the encounter. There is a subtle bonus hidden here. If Apophis turns out to be two rocks loosely joined together, a shape scientists suspect for some asteroids, then a sudden spin change could shift those two pieces relative to each other. The rock might actually rearrange its own body as it tumbles past us, its parts sliding into a new configuration. Watching for that would tell us whether Apophis is truly one rock or secretly two. That possibility, that Apophis might be double, opens a whole new mystery. Because a surprising number of asteroids are hiding a companion quietly stuck to their side, and Apophis may be one of them. When you picture an asteroid, you probably imagine a single lump of stone. Many asteroids match that picture, but space holds a stranger kind of object, and scientists suspect Apophis might be one of them. Some asteroids are not one rock at all. They are two stuck gently together, touching at a single point like two pebbles resting side by side. Scientists call this a contact binary. Picture a peanut still in its shell, with two rounded bulges joined by a narrow waist. That is the classic shape of a contact binary. Two separate bodies, drawn together over long stretches of time by their own faint gravity, drifting closer and closer until they finally kiss and stay joined. They do not merge into one solid mass, they simply lean against each other, held in a loose embrace by the weakest of forces. How do two rocks end up glued together this softly? Out in space, objects move slowly relative to one another, and gravity works patiently. Two asteroids can approach so gently that when they finally meet, they do not smash apart. They settle against each other and remain balanced for ages. A surprising number of the asteroids we have studied up close have turned out to wear this double shape, so the idea is far from far-fetched. The clues about Apophis come from its tumble and its shape. Studies of how it reflects light hint at a body that is elongated, stretched out rather than round, exactly what you would expect from two lobes joined at a waist. Its restless, wobbling motion also fits a lopsided object with its weight spread unevenly, the kind of thing two joined rocks would produce. None of this is proof. It is a strong suspicion, waiting to be confirmed. If Apophis really is two rocks in a gentle embrace, the flyby becomes even more dramatic. Remember, Earth's gravity might change the asteroid's spin, speeding it up or slowing it down. For a contact binary, a change in spin could do something remarkable. It could shift the two pieces relative to each other. The narrow point where they touch is their weakest link, and a sudden twist could make the two lobes slide, rock, or resettle into a new position. Imagine watching that happen. A rock that has held its peanut shape for ages, brushing past Earth and coming away with its two halves subtly rearranged. The asteroid would reshape its own body in front of our instruments, driven by nothing but our planet's passing pull. Few sights in space science would be stranger or more revealing. That is why confirming the double nature of Apophis matters so much. Whether it is one solid rock or two loosely joined ones changes everything about how it will respond to the flyby, and everything about how we might one day deflect an asteroid like it. A solid rock takes a push cleanly. A pair of joined rocks might come apart under the same shove, which is the last thing you want when trying to protect Earth. So the question of one rock or two is not idle. It reaches all the way to the future of planetary defense, and answering it is one of the great goals of the missions racing toward Apophis. But the asteroid's shape and spin are not the only forces steering its fate. Out in the dark, a far quieter influence has been nudging Apophis for years, using nothing more than sunlight. Something has been pushing Apophis for years, and it is not gravity. It is light. The gentle warmth of the sun falling on the asteroid day after day has been quietly nudging the rock along a slightly different path than gravity alone would set. It sounds impossible that sunlight could shove a mountain of stone through space, yet it does, and scientists have measured it with astonishing precision. The trick works through heat. As Apophis turns, sunlight warms one side of the rock. That warmed side then rotates away and slowly radiates its heat back into space as the asteroid spins. Here is the subtle part. When a warm surface throws off heat, it also gives itself the tiniest push, like a gentle exhale of energy leaving the rock. Because the asteroid spins, this little push always comes from the same direction, and over years it adds up into a steady, faint force nudging the whole asteroid along its orbit. Scientists call this the Yarkovsky effect. Any single push is laughably small, far too weak to feel, but space is patient, and the pushes never stop. Day after day, year after year, the asteroid radiates its heat and receives its endless series of tiny nudges. Over decades and centuries, those whispers of force add up, gradually shifting the asteroid's path around the Sun. A rock steered, ever so slowly, by the warmth it gives off. For Apophis, scientists have pinned down this feeble force with remarkable accuracy. In fact, the Yarkovsky effect has been measured more precisely for Apophis than for almost any other asteroid in the sky, second only to one other well-studied rock. That precision was hard-won, drawn from years of careful tracking, and it matters enormously. Here is why. When you're trying to predict where an asteroid will be decades from now, even the tiniest force becomes important. A push too small to notice today can grow, over many years, into a shift of thousands of miles in the asteroid's future position. During the frightening early days of Apophis, this gentle sunlight force was one of the wild cards that made its distant future so hard to nail down. To rule out any impact for 100 years, scientists had to account for it exactly. So this quiet nudge is a hidden hand on the asteroid's path, and knowing it precisely is part of how we gained confidence that Apophis will miss us. The same force that could have tipped it toward danger once measured became a reason for reassurance. We understand the push, so we can predict the path. The Yarkovsky effect steers the asteroid's journey around the Sun, its slow drift through space. But sunlight has a second, sneakier trick, one that reaches not the asteroid's path but its spin. The very same heat that nudges Apophis along its orbit is also, little by little, winding up the way it turns. Sunlight does more than nudge Apophis along its path. It also reaches into the way the asteroid spins, slowly winding it up or slowing it down over vast stretches of time. It is a close cousin of the effect from the last chapter, born from the same source, the gentle push of heat leaving a warm surface, but instead of moving the whole rock through space, this one twists it. Scientists call it the Yorp effect, a tidy name standing in for a long string of researchers who worked it out. Here is how it turns a rock. An asteroid is never perfectly smooth or perfectly round. It has bumps, ridges, slopes, and uneven faces. When sunlight warms these lopsided surfaces and they radiate their heat back into space, the little pushes do not cancel out evenly. On an irregular rock, they can add up into a gentle twisting force, a torque that nudges the asteroid to spin a little faster or a little slower, depending on its exact shape. Sunlight catching on the rough edges of a rock becomes a hand that turns it. Like its cousin, any single push is almost nothing. But across millions of years, the effect is powerful. YORP can gradually speed up an asteroid's spin until it whirls dangerously fast, or slow it down until it nearly stops and begins to tumble. Many scientists believe this slow twisting by sunlight is one of the main reasons asteroids end up spinning the way they do, and even why some of them wobble and tumble instead of turning cleanly. That points straight back to Apophis. Remember its strange, restless tumble, that off-kilter rolling motion with its two mismatched clocks. The YORP effect is a leading suspect for how the asteroid ended up in such a disturbed state. Over ages, sunlight may have slowly twisted Apophis out of a clean, simple spin and into the complicated wobble we see today. The tumble could be the long, patient work of light itself. This deepens the mystery in a lovely way. Two invisible sunlight forces have been shaping Apophis all along. One steers its journey around the Sun, the other winds its spin and may have set it tumbling. Neither force is strong enough to notice in a single day, yet across the deep well of time, together they have quietly sculpted the asteroid's motion, path and spin alike. There is a practical catch buried here, and it made the early predictions of Apophis harder. Because Yorp slowly changes the spin, and because the spin affects the other sunlight force steering the orbit, The two effects tangled together over long timescales. Untangling them, measuring each precisely, was part of the enormous effort to predict where Apophis would be far in the future. Only by understanding these faint forces could scientists gain full confidence in the asteroid's path, and gaining that confidence required watching Apophis carefully, year after year. Yet there is a problem. For a long stretch of recent time, we could not watch it at all. The asteroid slipped into a hiding place in the sky, out of reach of every telescope on Earth. To predict an asteroid's path with confidence, you need to watch it often. Every new sighting sharpens the picture, tightening the known orbit and shrinking the uncertainty. So you might expect scientists to have kept a constant, unbroken watch on Apophis, the most famous, dangerous asteroid of its era. They could not. For several recent years, Apophis simply vanished from view. It was not lost. Scientists knew roughly where it was. The trouble was that it drifted into a region of the sky where no telescope on Earth could get a clear look. From around the year 2021 until close to 2027, Apophis became effectively unobservable, hidden away for a stretch of years right in the run-up to its famous flyby. Think about the strange timing. In the crucial years before the closest asteroid pass in recorded history, the asteroid itself went dark to us. We could not refine its position with fresh observations. We could not check for any subtle change in its path. We had to rely on the excellent measurements gathered earlier, especially the radar work that cleared it, and simply trust the math to carry us through the blind years. For scientists, that silence was uncomfortable. They knew Apophis would miss us, thanks to the precise tracking done before it disappeared. But the asteroid hunter's instinct is to keep watching, always. And here was a case where watching became impossible for years. The most closely studied rock in the sky, slipping into a stretch of darkness precisely when curiosity ran highest. This gap also raised a quiet, unsettling thought. If Apophis were disturbed during its hidden years, if something nudged it in a way we could not see, we would not know until it emerged again. The tracking done beforehand was thorough enough to give strong confidence in its path. Yet the blind window meant scientists could not directly confirm, in real time, that nothing had changed. They had to wait for the asteroid to return to view. That return will come as the flyby approaches. As Apophis draws near for its 2029 encounter, it will climb back into a part of the sky where telescopes can finally see it again. Astronomers will pounce on those first fresh sightings, eager to measure the asteroid anew and confirm that its path matches every prediction. The reunion, after years of silence, will be a moment of real anticipation. So why did Apophis disappear in the first place? It was not swallowed by distance or shadow in any ordinary sense. It was hidden by the one object in the sky too bright to look past. The asteroid drifted into the glare of the sun itself, lost in a flood of light we cannot see through, and that hiding place, the sun's blinding glow, exposes a dangerous blind spot in how we watch for asteroids, a direction we simply cannot guard. The reason Apophis vanished comes down to a simple, humbling limit. We cannot look at the sun. Its light is so overwhelming that any telescope pointed near it is blinded, drowned in glare. So when an asteroid drifts into that region of the sky, into the same direction as the sun as seen from Earth, it becomes hidden. Not by distance, not by darkness, but by too much light. For years, Apophis sat in that blinding zone. It rose and set close to the sun, buried in the daytime brightness, impossible to pick out. The asteroid was there the whole time, circling as always, but our telescopes could not cut through the glare to find it. The sun became a curtain, and Apophis waited behind it. This is more than a passing inconvenience for one asteroid. It reveals a genuine weakness in how we guard our planet. There is a whole direction in space that we cannot easily watch, the direction of the sun, and dangerous objects can hide there. An asteroid approaching Earth from the sun's direction comes at us out of the glare, unseen until it is very close, or even until it is too late. History has already shown us the danger. In the year 2013, a rock came screaming out of the daytime sky over Russia, with no warning at all. No telescope had spotted it, because it approached from the direction of the sun, swimming in that blinding light. It exploded above a city, and the shockwave shattered windows and injured over 1,000 people. Nobody saw it coming, precisely because it arrived through our blind spot. That event was a wake-up call. It proved that the sun's glare is not just an annoyance for astronomers. It is a real gap in our planetary defences, a doorway through which asteroids can slip undetected. And Apophis, by hiding in that same glare for years, quietly reminded scientists of the problem all over again. The good news is that scientists are working to close this blind spot. Plans are underway for space telescopes designed to hunt asteroids from vantage points where the sun's glare is less of an obstacle, watching the very region we cannot see well from the ground. The goal is to find dangerous rocks early, especially those sneaking in from the sunward side, so no future asteroid can surprise us the way the one over Russia did. Apophis, for its part, will soon step out of the glare. As it approaches for the flyby, it will move into darker sky and become visible again, ending its long hiding. Scientists will finally get to measure it fresh after years of forced silence, confirming its path as it races toward that historic close pass. But the blind spot leaves behind a lingering worry, a what-if that scientists have actually studied. During those unseen years, could something have happened to Apophis out there in the dark that we did not witness? Could an unnoticed event have nudged the asteroid? It sounds far-fetched, yet researchers have run the numbers on exactly that nightmare. Scientists are careful people, and part of being careful is imagining the unlikely. So even after Apophis was cleared of any danger for 100 years, one researcher asked a chilling question. What if something out there hit Apophis before it reaches us, knocking it onto a new and dangerous path? The idea works like this. Our predictions of where Apophis will go are only as good as our knowledge of its current path. That path was measured beautifully and it leads to a safe miss. But those predictions assume nothing disturbs the asteroid in the meantime. What if a small unseen rock, one we never detected, were to collide with Apophis somewhere along the way? A hard enough knock could shove the asteroid off its safe course and in the worst case toward Earth. An astronomer ran the simulations to test this fear, and the result offers real comfort. The odds of such a collision nudging Apophis into danger came out to roughly 1 in a million. Vanishingly small. To even matter, an undetected rock would have to strike Apophis at just the right moment, from just the right direction, with just the right force, a stack of coincidences so unlikely it barely registers as a possibility. So, the nightmare is not something to lose sleep over. 1 in a million means Apophis is, for all practical purposes, still perfectly safe. The study did not uncover a hidden threat. It confirmed how secure our predictions really are, even against the wildest bad luck. Yet the exercise was valuable for a subtler reason, and it ties back to the blind years. Remember that Apophis spent a long stretch hidden in the sun's glare, unwatchable. During that silence, scientists could not directly confirm moment to moment that nothing had touched it. Studies like this one helped fill that gap. By calculating how unlikely any disturbance would be, researchers gave themselves confidence to carry through the blind window without fresh sightings. The math stood in for the missing observations. There is a deeper lesson buried here, one that reaches beyond Apophis. It reminds us that our knowledge of the sky is always built on assumptions, and good scientists test those assumptions relentlessly, even the ones that feel safe. Asking what if something hits it first is not paranoia. It is the discipline of imagining every path, however unlikely, so that nothing catches us by surprise. The 1 in a million study is that discipline in action. This careful thinking also points toward the future of planetary defense. To truly protect Earth, we cannot only track the asteroids we know. We must also account for the ones we have not found, the small and hidden rocks that could, in principle, interfere. Every study like this sharpens our sense of what we still cannot see and where our watch needs to grow stronger. That brings us to a strange and important idea that sits at the very heart of Apophis and its future. There are certain tiny regions in space, invisible gateways that decide whether an asteroid will strike Earth on a later pass. Miss them and we are safe. Pass through one and the future changes. These gateways are called keyholes. Here is one of the most elegant and unsettling ideas in the study of dangerous asteroids. There are invisible regions in space, no bigger than a small patch of emptiness, that can decide whether an asteroid will one day strike Earth. Pass through one of these regions during a close flyby, and a future impact becomes possible. Miss it, and the danger evaporates. Scientists call these tiny, fateful patches keyholes. The idea grows directly out of everything we have learned about the flyby. When Apophis passes Earth, our gravity will bend its path, and exactly how much it bends depends on precisely where the asteroid passes. Fly by a little higher, and the orbit changes one way. Fly by a little lower, and it changes another. Most of these outcomes send Apophis onto a perfectly safe future path, but a few very specific outcomes could bend its orbit just so, setting it up to return and strike Earth on a later pass, years or decades down the line. A keyhole is one of those specific dangerous passing points. Picture a keyhole in a door, a small opening that a key must thread through exactly to turn the lock. In space, a gravitational keyhole is a small window the asteroid would have to pass through during its flyby to be nudged onto a future collision course. These windows are tiny, sometimes only a few hundred feet wide, floating in the vastness near Earth. The asteroid either threads that needle or it does not. This is where the story of Apophis becomes clearer. In the frightening early years, part of the worry was not just the 2029 pass itself, but whether Apophis might sail through a keyhole during that pass and set up a strike on a later date, on another loop around the Sun. Those distant possibilities, years beyond the flyby, were the faint question marks that lingered even after the first scare eased. The radar measurements settled it. By pinning down the asteroid's path with such precision, scientists could see that Apophis will not pass through any dangerous keyhole in 2029. It will thread safely past all of them, missing every window that could lead to a future impact. That is a large part of why the asteroid could be cleared for a full century. Not only does it miss us this time, it misses the hidden gateways that could bring it back to harm us later. The concept of keyholes is one of the great insights of planetary defense, and it changes how we think about protecting Earth. It means we do not only worry about whether an asteroid hits us on its next pass. We must also watch whether it threads a keyhole that sets up a hit further down the road. A safe flyby today could plant the seed of a strike tomorrow if the asteroid passes through the wrong point. This idea also carries a hopeful side, which we will return to later. If a keyhole is a tiny window, then keeping an asteroid out of it might require only the gentlest of nudges. But before we reach that hope, there is a reason the 2029 flyby matters so much for prediction itself. This one encounter will reshape everything we can say about the asteroid's future. The 2029 flyby is not only a spectacle and an experiment, it is also a turning point in our ability to predict the asteroid at all. This single close pass will reshape everything we can say about where Apophis goes next, and it will do so in a way that scientists find both challenging and thrilling. The reason lies in how predictions work. To forecast an asteroid's path, scientists rely on a chain of careful measurements gathered over years. Each measurement refines the picture, but a very close encounter with a planet throws a wild card into that chain. When Apophis whips past Earth, our gravity will bend and reshape its orbit so strongly that the asteroid's future path depends critically on the fine details of the pass. Tiny differences in how it flies by will grow into large differences in where it ends up afterward. This makes the flyby a kind of great divide in the asteroid's timeline. Everything before it, we know well. Everything after it depends on nailing the encounter itself with extreme precision. Scientists describe the encounter as acting almost like a fresh chapter of observation. Before the pass, our predictions of the far future carry some uncertainty, because small unknowns in the asteroid's motion and in those subtle sunlight forces have room to grow over time. The flyby sharpens everything. By watching exactly how Apophis behaves as it swings past Earth, and by measuring its path precisely on the way out, scientists will lock down its future orbit far better than they ever could before. In other words, the very event that scrambles the old predictions also delivers the data to build far better new ones. The flyby is both the disruption and the cure. Watch it closely enough, and Apophis becomes one of the best understood asteroids in the entire sky, its path charted with confidence for a very long time to come. This is why scientists are so determined to observe the encounter in exquisite detail. It is not only about the drama of the close pass or the changes to the surface and spin, it is about seizing a once-in-a-generation chance to measure an asteroid at the exact moment its future is being rewritten. Miss the fine details, and you lose the chance to predict Apophis cleanly for decades. Capture them, and you gain a precise map of its journey far into the future. There is a beautiful symmetry to it. Earth's gravity will reshape the asteroid's path, and by watching that reshaping, we will reshape our knowledge of the asteroid. The planet acts on the rock, and the rock in turn teaches us. A single afternoon of close observation could settle questions that would otherwise take lifetimes. To capture all of this, though, telescopes on the ground will not be enough. To truly witness the surface changes, the spin shifts, and the fine details of the pass, scientists need to be there, right beside the asteroid, watching from up close. And so, across the solar system, spacecraft are already on the move, racing to reach Apophis. One of them has done this before. It has already visited an asteroid, grabbed a piece of it, and sent that piece home. Now it has been given a new target. Reaching an asteroid takes years of planning, and a spacecraft built for the journey. Building one from scratch to catch Apophis in time would be nearly impossible. So scientists found a clever shortcut. They already had a spacecraft in space, one that had just finished an extraordinary mission, and they gave it a new purpose. The spacecraft began its life on a bold quest to visit a different asteroid, a dark rock named Bennu. It travelled there, studied it in detail, and did something remarkable. It reached down, touched the asteroid's surface, and grabbed a sample of dust and pebbles. Then it turned for home and, in the year 2023, dropped that precious sample down to Earth in a sealed capsule, delivering humanity a genuine piece of an asteroid to study in our laboratories. Its main job was done, but the spacecraft itself was still healthy, still flying, still full of capability. So mission planners asked a bold question. Instead of retiring it, why not send it to a new target? And the perfect target was waiting. Apophis, about to make the closest asteroid pass in recorded history. The spacecraft was given a new name to match its new mission, one that honours its journey from its first asteroid to its second. It became the Apophis Explorer, and it set off on a fresh course to rendezvous with the famous rock. There is a catch, and it comes from the hard rules of orbital motion. The spacecraft cannot arrive in time to watch the actual moment of closest approach. Because of the way orbits work, the paths of the spacecraft and the asteroid simply do not line up for an earlier meeting. So the Apophis Explorer will reach the asteroid a short while after the flyby, arriving roughly a month after Apophis has already swept past Earth. That timing shapes its role. The spacecraft will not witness the dramatic pass itself. Instead, it will show up in the aftermath, and that turns out to be enormously valuable. It will study Apophis after the encounter, examining an asteroid freshly disturbed by Earth's gravity. Any quakes, any landslides, any shifts in spin or surface, the Apophis Explorer will be there to inspect the results up close, reading the fresh scars of the flyby. And it will not simply glance at the asteroid and leave. The plan calls for the spacecraft to settle in and study Apophis for a long stretch, orbiting the rock and mapping it in fine detail over many months. It will get to know this world intimately, tracing every feature of a surface that may have just been reshaped before its arrival. But arriving after the flyby means the spacecraft will miss the changes as they happen. It can only study the aftermath. To catch the transformation live, in the very moment Earth grips the asteroid, someone would need to be there beforehand. And the spacecraft has one more trick planned for when it does arrive, a bold maneuver to peer beneath the surface itself. When the Apophis Explorer finally reaches its target, it will not settle for studying the surface from a polite distance. It has a bolder plan, one designed to reveal what lies hidden just beneath the asteroid's skin. The spacecraft will get up close and deliberately stir things up. The idea is both simple and daring. The spacecraft will descend toward the surface of Apophis and fire its engines directly at the ground. The blast of gas will kick up loose rocks and dust, blowing away the top layer and exposing the material just underneath. It is a way of peeking below the surface without ever landing, using the spacecraft's own engines as a tool to sweep the asteroid's face clean. Why go to such trouble? Because the surface of an asteroid and its interior can be very different. The outer layer has been exposed to space for ages, weathered and altered by sunlight and radiation. The material a little deeper down is more pristine, closer to the asteroid's true original makeup. By blowing away the weathered top, the spacecraft can reveal fresher rock and study what Apophis is really made of underneath. This connects directly to one of the asteroid's deepest mysteries, the puzzle of its young-looking face. Recall that Apophis appears strangely fresh, as if its surface keeps getting renewed. By kicking up the surface and comparing the exposed material to the weathered top, scientists can learn how deep that weathering goes and how the asteroid's skin has changed over time. The engine blast becomes a probe into the asteroid's history. There is a lovely echo here with the flyby itself. Earth's gravity might resurface Apophis by shaking loose its material during the close pass. Then the spacecraft, arriving afterward, will do a small, controlled version of the same thing, disturbing the surface on purpose to see what lies beneath. Nature and machine, each stirring the asteroid to reveal its secrets, one on a grand scale and one up close. The maneuver also serves the larger goal of planetary defense. To protect Earth from a dangerous asteroid one day, we need to understand what these rocks are made of, not just on the surface, but throughout. A solid rock and a loose pile of rubble would need very different strategies to deflect. By probing beneath the surface of Apophis, the spacecraft gathers exactly the kind of knowledge we would need to push a threatening asteroid off course safely. So the Apophis Explorer will do more than observe. It will interact, reaching out to touch and stir the asteroid, turning itself into an active investigator rather than a passive watcher. Its long study, combined with this bold maneuver, will teach us an enormous amount about a world we can barely see from Earth. Yet for all its cleverness, the spacecraft carries one great limitation. It arrives too late to witness the flyby as it unfolds. To capture the transformation live in real time, another spacecraft would need to be waiting at Apophis before Earth ever grips it. And across the ocean, a different space agency is racing to build exactly that. To witness the flyby as it happens, a spacecraft must reach Apophis before the asteroid meets Earth, not after. The spacecraft already on its way will arrive too late for the main event. So a second team at the European Space Agency set out to solve that problem with a mission of its own. Their goal is simple to state and hard to achieve: get there first. Their mission carries a name drawn, fittingly from ancient Egypt, matching the asteroid's own mythic naming. It is a mission built for speed, designed to rendezvous with Apophis and accompany it through the flyby, watching the whole encounter unfold from a front row seat right beside the rock. The plan is to arrive at Apophis about 2 months before the close pass. In those weeks beforehand, the spacecraft will study the asteroid in fine detail, building a complete portrait of what Apophis looks like before Earth touches it. Its shape, its surface, its spin, all recorded carefully in advance. This becomes the crucial before picture, the baseline against which every change will be measured. Then comes the main event. As Apophis sweeps past Earth, the spacecraft will be right there, watching in real time. It will observe the asteroid during the flyby itself, capturing the quakes, the landslides, the shifting surface, and the changing spin as they happen, moment by moment. If Apophis transforms in that narrow window near closest approach, this spacecraft will see it live, something no telescope on Earth could ever fully capture, and it will keep watching afterward, recording the after picture too, before, during, and after, all from up close. The spacecraft will build a complete story of the encounter, the first time humanity has ever watched a planet reshape an asteroid in real time from right beside it. This mission carries a purpose beyond pure science, and it is a serious one. It is meant to prove that we can build and launch a spacecraft to reach a threatening asteroid quickly, in just a few years. Think about why that matters. If we ever discover a rock truly headed for Earth, we may not have decades to prepare. We would need to send a spacecraft fast to study the threat and figure out how to stop it. This mission is a rehearsal for that exact scenario, a test of whether we can respond in time. To move quickly, the team is reusing technology and designs from earlier missions rather than building everything new. This is how they can meet the tight deadline set by the flyby, which will not wait for anyone. The asteroid arrives on its own schedule and the spacecraft must be ready. Together, the two spacecraft form a powerful team. One arrives before the flyby to watch it live, and the other arrives after to study the aftermath in long detail. Between them, they will capture the full transformation of Apophis, from the calm before to the changed world after. And the mission arriving first will carry tiny helpers with it, small companions that will spread out and watch the asteroid from more than one angle at once. The spacecraft racing to reach Apophis first will not travel alone. Tucked aboard it will be small helpers, tiny satellites that will ride along for the journey and then break away to watch the asteroid from their own vantage points. These little companions are called CubeSats, and they show how much space science has changed. A CubeSat is a spacecraft shrunk down to a remarkably small size, built from compact standardized units rather than one huge custom machine. Where older spacecraft were the size of cars or vans, these tiny craft can be small enough to hold, packed with miniature instruments. They are cheap enough and light enough to send several at once, and that changes what a mission can do. The plan for Apophis is to carry a pair of these small satellites and release them near the asteroid before the close pass. Once free, they will operate on their own, spreading out to observe Apophis from angles the main spacecraft cannot reach by itself. Instead of one set of eyes on the asteroid, the mission will have several, watching from different positions at the same time. Why does that matter so much? Because the flyby will unfold quickly, and it will unfold in 3 dimensions. A single spacecraft can only see one side of the asteroid at a time, but if quakes ripple across the surface, or a landslide slips down one face, you want eyes everywhere, catching the action from multiple directions. The little companions turn the mission into a small fleet, able to watch the whole event more completely than any single craft could. There is a beautiful logic to this approach. Rather than betting everything on one enormous expensive spacecraft, the mission spreads its watching across a team of large and small craft working together. The main spacecraft brings its powerful instruments. The tiny companions add extra eyes and extra angles. Together they cover far more than any one of them alone. This small satellite strategy also fits the mission's need for speed. Building tiny spacecraft is faster and cheaper than building giant ones, which helps the whole mission meet its tight deadline. In the race to reach Apophis before the flyby, every advantage counts, and small, quick-to-build companions are a real advantage. The CubeSats represent something bigger too. They hint at how we might explore and defend against asteroids in the future, not with a single grand spacecraft, but with nimble teams of small craft that can be built quickly and sent in numbers. If a dangerous asteroid ever appeared, this kind of fast, flexible fleet could be exactly what we need to study it in a hurry. So when Apophis makes its historic pass, it will be met by a small gathering of human machines, a main spacecraft and its tiny helpers, all watching together. And between this fleet arriving before the flyby, and the other spacecraft arriving after, humanity is about to accomplish something it has never done before. We will capture the complete story of an asteroid being transformed, put all the pieces together, and something extraordinary comes into focus. For the first time in history, humanity is going to capture the complete story of an asteroid being reshaped by a planet, from beginning to end, up close. This has never been done before, and Apophis will be the star of the film. Think about what the 2 missions accomplish when combined. One spacecraft and its tiny companions arrive before the flyby, recording exactly what Apophis looks like in its undisturbed state, then watching live as Earth grips it. The other spacecraft arrives afterward, settling in to study the changed asteroid in long, patient detail over many months. Between them, they cover the entire event, before, during, and after. That completeness is the breakthrough. Scientists will not have to guess what changed by comparing scattered snapshots. They will have a genuine before and after record of the same asteroid, watched continuously through its transformation. Whatever Earth's gravity does to Apophis, whether it triggers quakes, unleashes landslides, refreshes the surface, or alters the spin, we will see it captured from up close, start to finish. This turns Apophis into a natural experiment of astonishing power. Nature is providing the setup, a giant asteroid passing close enough for a planet to reshape it, on a date known years in advance. Humanity is providing the cameras, a fleet of spacecraft positioned to record every stage. No laboratory on Earth could ever recreate this. You cannot build a machine to squeeze a real asteroid with a planet's gravity. You can only be ready when nature does it for you. The scientific payoff will be immense. By watching how Apophis responds, scientists will finally answer questions that have lingered since the asteroid was discovered. Is it one solid rock or a loose pile of rubble? Is it a single body or 2 joined together? How does its surface renew itself? How does a close pass change an asteroid's spin? Each of these mysteries could crack open in the light of a well-watched flyby. There is a poetic weight to the moment too. Apophis began as a source of fear, a god of chaos threatening our world. Now it becomes a teacher, offering humanity its clearest look ever at how asteroids behave when a planet reaches out to touch them. The rock that once frightened us will, through careful watching, teach us more about asteroids than almost any object before it. And this knowledge arrives at exactly the right time. We live in an era when humanity has finally begun to take seriously the threat of asteroids and to build the tools to defend against them. Understanding how a real asteroid responds to a real gravitational encounter is precisely the kind of knowledge we need. The film we capture of Apophis will not only satisfy our curiosity, it will help us protect our planet. Because everything we learn from this flyby feeds into a larger mission, one that may someday matter more than any single asteroid. The 2029 encounter is, in the end, a rehearsal. A practice run for the day we might have to save the Earth. Strip away the spectacle and the science, and the Apophis flyby reveals its deepest purpose. It is a rehearsal. A practice run for the day, perhaps far off, perhaps not, when humanity discovers an asteroid truly headed for Earth and has to do something about it. For almost all of history, we were helpless against this threat. If a large asteroid were on a collision course, we could only watch it come. That has finally begun to change. In recent years, humanity crossed a remarkable threshold. We proved for the first time that we can actually move an asteroid. The proof came from a bold experiment. Scientists sent a spacecraft to deliberately crash into a small asteroid, one that posed no threat to us, simply to see if the impact could shift its motion. It worked. The collision nudged the asteroid, measurably changing its path. For the first time, humanity had reached out and altered the course of another world. We were no longer helpless. We had a tool. Apophis extends that lesson in a new direction. Crashing into an asteroid proves we can push one. But to push the right way, at the right time, we first need to understand what asteroids are made of and how they behave. A solid rock responds to a shove differently than a loose pile of rubble. An asteroid's spin, its structure, its strength, all of these shape how we would deflect it. Apophis, studied up close during its flyby, will teach us these very things. The missions racing to the asteroid carry this defensive purpose at their core. One of them exists partly to prove we can build and launch a spacecraft quickly, reaching a threatening asteroid in just a few years. That speed could be everything. If we ever spot a real threat, we may not have long to act. Being able to respond fast, to send a scout and then a solution, could mean the difference between deflecting an asteroid and suffering its impact. There is a comforting truth woven through all of this. The threat of asteroids, once a source of pure dread, has become something we can study, prepare for, and act against. We are no longer passive targets waiting for the sky to fall. We are becoming a species that watches the heavens, understands what we see, and stands ready to defend our home. Apophis is a milestone on that journey. The elegance of asteroid defense adds to the hope. Remember the keyholes, those tiny windows an asteroid must thread to strike us on a future pass. If danger comes down to threading a small window, then avoiding it might take only the gentlest push, applied years in advance. A tiny nudge, delivered early, could grow over time into a wide, safe miss. We may not need to blast an asteroid apart. We may only need to tap it softly at the right moment. But that hope carries a warning inside it, one that scientists take very seriously. Pushing an asteroid is delicate work, and doing it carelessly could make things far worse. Because if an asteroid is a loose pile of rubble, a clumsy shove might not move it cleanly. It might break it into pieces. Deflecting an asteroid sounds straightforward. Give it a push, move it aside, save the Earth. But there is a hidden danger in that simple picture, and it is one of the most important lessons hiding inside the study of Apophis. Push an asteroid the wrong way, and instead of moving it aside, you might shatter it. The risk comes down to what asteroids are made of. If a threatening asteroid were a single solid rock, you could shove it cleanly, and the whole thing would move together as one piece. But many asteroids are not solid at all. They are rubble piles, loose heaps of boulders and dust held together only by their own faint gravity. And a rubble pile responds to a shove very differently than a solid rock does. Imagine trying to push a loose pile of gravel across a table with a sudden hard shove. The pile does not slide neatly, it scatters. Now imagine that gravel pile is an asteroid headed for Earth. A clumsy, forceful push could break it apart into several pieces, and those pieces might spread out, some still heading toward our planet. Instead of one threat, you could create many. A single incoming rock could become a scattered swarm, and that could be far more dangerous than the original. This is why understanding an asteroid's structure matters so desperately for planetary defense. Before you push a real threat, you need to know whether it is a solid rock you can shove confidently or a fragile rubble pile you must nudge with great care. Get it wrong, and your attempt to save the Earth could make the danger worse. Apophis sits at the heart of this question. Scientists still do not fully know whether it is solid or loose, one rock or two joined together. The flyby and the spacecraft studying it are designed to answer exactly this. By watching how Apophis responds to Earth's gravity, and by probing its surface up close, we will learn how this kind of asteroid holds together. And that knowledge tells us how to push one safely, should we ever need to. The gentle approach to deflection makes even more sense in this light. A soft, early nudge, applied years before any impact, avoids the danger of shattering entirely. You're not slamming the asteroid hard. You're giving it a patient, steady push, letting time turn that small change into a wide miss. This careful strategy protects against breaking the very rock you are trying to redirect. So the study of Apophis carries a quiet wisdom. It teaches us not only that we can move asteroids, but that we must do so thoughtfully, with full knowledge of what we are pushing. Reckless force could backfire. Careful understanding is the real key to defending our planet. The flyby is a lesson in humility as much as power, and there is one final gift that Apophis offers, beyond the spectacle, beyond the science of defense. This ancient rock is a messenger from the deepest past, carrying within it the story of how our entire solar system began. For all the fear it once caused and all the science it now offers, Apophis holds one final gift, perhaps the most profound of all. It is a messenger from the dawn of time, carrying within its ancient rock the story of how our solar system was born. To study Apophis is to read a page from the very beginning of everything. Asteroids are the leftover building blocks of the solar system. When our sun and planets formed, they emerged from a vast cloud of gas and dust that slowly gathered into worlds. Most of that material became the planets we know, but some of it never finished the job. Scattered chunks were left over, drifting through space, never gathered into a planet. Those leftovers are the asteroids, and Apophis is one of them. This makes Apophis unimaginably old. It formed alongside the planets more than 4 billion years ago, in the earliest days of our solar system. It has drifted through space ever since, largely unchanged, a frozen relic from a time before Earth had oceans, before life, before anything we would recognize. Holding that in your mind changes how you see the faint dot in the sky. You are looking at something older than the ground beneath your feet. Because asteroids are so ancient and so little changed, they are like time capsules. The planets have been transformed over billions of years by heat, weather and geology, their original material reshaped beyond recognition. Asteroids escaped most of that. They preserve the raw ingredients of the early solar system in something close to their original form. Study an asteroid, and you study the past directly, reading materials that have barely changed since the beginning. This is why scientists treasure the chance to examine Apophis up close. When the spacecraft study its surface, probe beneath its skin, and analyze what it is made of, they are not only learning about one rock, they are learning about the conditions that gave birth to our entire solar system. What was the early solar system made of? How did the planets come together? Asteroids like Apophis hold clues to these deepest questions. There is even a chance that asteroids carry clues to our own origins. Some asteroids contain the kinds of molecules that form the basic ingredients of life, and many scientists suspect that asteroids and comets may have delivered water and those key ingredients to the early Earth. If so, then rocks like Apophis are not only relics of the past, they may be connected to the very story of how life on our planet began. The messenger from the beginning may carry news about us. So Apophis completes a remarkable journey in our understanding. It arrived as a god of chaos, a source of dread, an asteroid that might end cities. It became a scientific treasure, an experiment we could never build ourselves, a rehearsal for defending our world. and in the end, it reveals itself as a messenger from the birth of the solar system, an ancient traveller carrying the story of where we all came from. On the night of April 13th, 2029, when you step outside and find that faint moving light drifting among the stars, remember all of it. You will be watching a piece of the beginning, closer than our own satellites, changed by our planet's touch, teaching us how to protect ourselves and where we came from. Look up and witness the closest visitor in recorded history.